Good afternoon, everyone. Welcome to Takeo Tuesday. Another fine presentation by the commercial training team of Brett Zerba and the famous Rich Medairos. Hopefully all of you or most of you know who we are. We've been doing this for way too long, but we're enjoying it. Quite a few of you answered some of Rich's questions that he wrote on his board, so that's great. So anyways, congratulations. So today's presentation is going to be as Rich's screen shows, introduction to hydraulic separators or separation. It's a different type topic, maybe primary, secondary, but there's other reasons you might be using it too not nowadays as well. So just keep that in mind. As most of you know, that you will be getting a email about 24 hours after today's presentation, and that will have access to today's webinar from a video, or it is being recorded, and access to your PDH hour credit. So if you need that, that does show up about 24 hours as an email. If there's any issues, you can always contact one of us or the Takeo folks, and you should be able to get it. So as most of you know, Takeo is a privately held company celebrating 102 years. Third generation. Johnny White Jr. is the current president. Rich and I had a Takeo University class last week in-house, and Johnny popped in. So he loves to spend time with groups that come and visit Takeo at the headquarters in Cranston, Rhode Island when he's available. When he's available, he travels quite a bit, but please, if you have some inklings to come in to a Takeo University class, get in touch with your local Takeo rep, and maybe something can be worked out. We periodically have those. Actually, between now and October, I think we've got 6 or 7 of them coming up. So feel free. By the way, there are 3 handouts available. If you'd like some handouts, they are catalogs of some of the equipment Rich will be talking about later during this presentation. So keep that in mind. Let's see, what else should I say? I don't think we need to talk too much about what's happened in the past. I know our production folks are working their tails off as material comes in. It's a crazy world, as most of us know out there, but they are doing an outstanding job, and we can't thank them enough for their efforts. And by the way, the Takeo factory located in Cranston, Rhode Island, is air conditioned. So that's some 200,000 square feet of cool air out there for the team that assembles all the products that you folks specify. Basis of design, and install. Some of you, I'm sure, are installers out there as well. So
yeah, the temperature, I guess, this week, Brett, is supposed to go up to 100 degrees.
Yeah, Thursday.
The Boston area, that's pretty amazing.
Yeah, last week when I gave the tour of our factory on Thursday afternoon, it was 90 plus outside, pretty humid out, probably in the 60% range, and the factory was very comfortable, very comfortable, and that was a big investment for Takeo, and that's some of the insight as to what they invest in, to help our production folks. Obviously, they invest in equipment and on an ongoing basis, new acquisitions, but they do also strive to take care of their employees, and the workforce is much for the better because of something like that. So, as you can only imagine. Again, I will be monitoring today's questions. I'll the moderator. Rich Medairos will be presenting. I'm going to turn it over to him very shortly. He can introduce himself and tell you that he's been working in the industry for a few years, although he did start at a relatively young age. Anyways, I think I'm done yapping. I think I've told everything. I'm assuming you can hear us and see. I know you can see the screen because many of you typed in when Rich was prior to us going live. So we're going to move forward. If you couldn't hear us, I'm sure some of you would start doing something, or raising your hand, or typing in questions, or whatnot. And by the way, thank you, David. Thank you, Ryan. please ask questions. That's one of the best ways for all of us to learn is how when people ask questions. And Rich and I appreciate the questions. It helps us with our presentation. It helps us learn, and it helps everybody learn, to be quite honest. And I think that's an important segue. So, Rich, take it away.
Well, thanks, Brett. I was just looking at the number of attendees. We're over 180 right now. That's great. So a quick introduction for myself. My name's Rich Medairos. I'm one of the senior systems engineers here at TACO, and I specialize in the engineering design of HVAC systems. And I've been doing it for several years, as Brett mentioned. And I am a PE registered in several states. So we're going to get right into our hydraulic separator discussion today. And what we're going to do, hopefully I can do this. Let's see if it advances. Yeah, look at that. Son of a gun. So what is hydraulic separator? What is a hydraulic separator? Where is a hydraulic separator used? How to size a separator? And we say questions, but as Brett mentioned a moment ago, you don't have to wait till the end of the presentation. You can type in your questions and Brett will ask me to pause periodically and we'll get into it. I do want to load up on the screen here my whiteboard, so bear with me 1 second. I had something else up on the whiteboard earlier today, so I'm going to have to select a clean sheet. We'll see what happens here. Try to do this. Try this one more time, Brett. Put up a new clean whiteboard. Look at that.
Looks clean.
Looks clean, doesn't it?
It's configuring though. Uh-oh.
It's configuring. Yeah. I know it's always weird when there it is. Look at that.
I like it.
So we're going to come back to this screen in a second, but let's go back here to the presentation material. So we already went through our intro, and so let's answer the first question. What is a hydraulic separator? And I like to put this up here because it turns out that, and we will get into the technology in a minute, but I like to put this phrase up here, hydraulic separator by any other name. It turns out there are multiple names for this phenomenon or component or device or configuration. It's called a bridge. It's also called a decoupler, zero pressure bypass, closely spaced tees, low loss header, twin tees. So those are all the different names that we use for hydraulic separators. And maybe you have some other phrases that you've heard out there, but we're going to go through this and talk a little bit about, before I actually go through this diagram, I'm going to go back to my whiteboard here, see if I can do that without messing things up. There's the hey, Brett, can you see the whiteboard okay?
I can.
So let's talk a little bit about a primary secondary loop. So if we had, let's say we had a chiller, I'm just going to put CH over here for chiller, and then we had a pump. We have a little circle with a triangle in it. That's the symbol that we use here for pump. And this is an oversimplified. What's that we say all the time, Brett? Don't do this at home. Don't try building this. This is for instructional purposes. This is sometimes referred to as the primary circuit, so we'll label that primary. And when we can take a pipe off here, go to another pump, and then let's just say that it feeds a load. That load could be almost anything. In our simple example here, I'll put a couple of arrows so you'll know which way the flow is going. This way here, back and forth. Okay, and this circuit on the right, so here's the load. There's the load over there on the right. And this is the secondary circuit. ARY, look at that. And this little guy right in the middle here is the hydraulic separator, known as the bridge. So I'm going to erase that little squiggly line. I just want to kind of point that out to you. Hey, look at that. That actually worked. That's really great. So
wow,
the theory here is
on a roll today.
I know it. This is unbelievable. So let's assign a flow to our system. Let's say in the primary side we had 1,000 gallons per minute. We're going to make that at a constant flow of 1,000 gallons per minute. And let's say that initially our secondary pump is off. Let's look at that first and see what happens here. So when the secondary pump is off, the flow travels through our bridge in this direction here. And we say that where the first connection is here to the second connection, that differential pressure, let's just write that down here, delta P, is approximately equal to 0, which is sometimes where we come up with that phrase, a zero pressure bypass. So our primary circuit is running at 1,000 gallons per minute. Right now, the pump for our secondary circuit is off, so all the flow is going across the bridge, just like I drew the arrow here before. But the pressure drop from this point of the first connection over here, we'll call that connection A, and this connection down here, B, is approximately equal to 0. And as long as that pressure drop is approximately equal to 0, that means there will not be any flow induced in the secondary circuit. Now, in the world of piping, there's no such thing as zero pressure drop, but is very, very close. And the whole idea when you design a primary secondary loop and you design a bridge is to make that pressure drop negligible or as close to 0 as possible. And that way, there will be no flow directed into the secondary circuit. So far, so good. Anybody have any questions about that basic concept of the zero pressure bypass?
Yes, there is a question. I believe it's from one of our good friends at TACO, Mario. Is there a maximum distance separating the two T's for hydraulic separation to operate properly?
Well, actually, there is a rough sort of number. Most people will say that that distance should be approximately 10 pipe diameters. So I'll put that in here, 10 pipe diameters. Sometimes we make a diameter circle with a slash line through it. So 10 pipe diameters. So if this was, let's say we were running 1,000 gallons per minute. Let me just, I have a little chart here that I'm going to look up in a second. So if I have 1,000 gallons per minute, so I'm going to go back here, put in 1,000. And I'm running a pipe that's approximately 8 inches, well, not approximately, let's say I had an 8-inch pipe. My velocity would be about 6.42 feet per second. And my pressure drop would be about 2.18 feet per 100 feet. So you can see that the pressure drop at about 2 feet, if this was 10 pipe diameters, and we just said this was 8-inch pipe, so that means that it would be an 80 inches. And 80 inches is what? About, well, let's see. How many, what is the distance of 80 inches? Well, let's just look here.
6 times 12 is...
It's about, just about 7 feet. So the pressure drop would be about, what did I say that pressure drop was a second ago? It'd be about 2.18 feet per 100 feet. So 2.18 divided by 100 times 7, the actual pressure drop would be about 0.15 feet. So as you can see that the pressure drop is approaching 0. So that's where the general rule of thumb is about 10 pipe diameters. Now, in the real world, we know that we may have to shorten that down a little bit, but in order to ensure there's a balance between the velocity and the mixing, we want to have a high enough velocity across the bridge so we don't get any mixing, but not too high a velocity so that we create a pressure drop. But generally speaking, 10 pipe diameters is usually a good number to start with. Hopefully I answered that question, Brett.
Yep.
Okay. So now let's look at our, let's look back at our piping system that we had up here a second ago. Let's see if we can do this without messing it up here. We go back to our piping. Oops, there it is. Hey, look at that, Brett. Okay, so here we have about 1,000 gallons per minute. That's roughly, well, it's closer to 1,200 gallons per minute. Let's just circle this up here and say it's about 1,200 gallons per minute. We're going to use that number, 1,200 gallons per minute. I'm going to round it off. And let's say that the primary circuit, again, this is the primary circuit on the left, and this is the secondary circuit on the right. And let's look at a couple of different cases. Let's look at the flow for the primary circuit. Let's say the primary circuit flow is equal to the secondary circuit flow. I'll just kind of make a little note down here. So in other words, I've got my primary pump that's pumping about 1,200 gallons per minute, and my secondary pump is pumping 1,200 gallons. So the flow comes around the corner here, and then it comes and then it peels off and it goes in this direction because my secondary pump runs back, and then it comes back at 1,000 gallons per minute. I'll write that over here. And let's see, it goes around the corner here at 1,000. And so the pressure, the flow across the bridge, in this case, is 0 gallons per minute. So the first case is when the primary flow is equal to the secondary flow and we get 0 flow across the bridge. That should be pretty straightforward. The second case, oh, and let's just think in terms of the temperature. Let's assume that the water temperature is 44 degrees Fahrenheit coming in this direction. That means it peels off and it goes to our load at 44. That's what that number represents. Comes back at, over on the right side, let's say, comes back at 54, and so we get 54 degrees Fahrenheit over here. Kind of ignore these temperatures over here because they don't really apply to our little simplified example.
Hey, Rich. Okay. Hey, yes. Rich. A couple of people are mentioning they think that you may have written something incorrectly. It might, instead of 1,000 in the secondary, it might be, did you mean 1,200?
Yeah. I'm glad someone picked up on that. So yeah, that should be 1,200. I'm sorry, the 1,200 comes around the corner, 1,200 goes in the secondary circuit, and 1,200 comes back.
I know you did that on purpose to see if anyone was awake out there.
Well, thanks for that that reasoning, Brett. I appreciate that. Okay, so that was when the primary circuit was equal to the secondary circuit. And let's do a different one here. Let's assume for a moment, again, we're starting with 1,200, rounds the corner here. But this time, we don't need 1,200 in the secondary circuit. Let's say the demand on the secondary side is only 600 gallons per minute. Whoops, 600. So it goes out here at 600, goes through the load, comes back at 600. And because we had 1,200 in the primary circuit, we're going to peel off 600. That means that across the bridge, we're going to wind up with 600 gallons per minute. So we're going to have 600 across the bridge here. And that 600 plus the 600 coming back from the secondary circuit is going to be equal to 1,200. So that is the case where the primary circuit, let's say the primary flow, is greater than the secondary flow. So that's case number 2. So case number 1 is when the primary flow is equal to the secondary flow. And the second case is when the primary flow is greater than the secondary flow. Or let's say that in reverse. The secondary flow is less than the primary flow. Okay, any questions about the case number 2? Let's just
Stanley mentioned that.
I lost you there, Brett.
Hello, Rich?
Yes, I can hear you now. Go ahead.
Am I back or not? Can you...
Yes, you're back.
Okay, all right. So Jim is asking, actually Rick is asking, is there a way to verify what's across the bridge?
Well, if you put in a flow meter, you can find out what the flow is across the bridge, or you can put a flow meter either in the bridge itself, or you could put it into the primary circuit. Let's say I put a flow meter over here, flow meter FM. And I also put a flow meter in the secondary circuit. Let's say I put a flow meter down here, FM. So the difference between those two would be what's going across the bridge. Now, as long as the primary circuit was greater than the secondary circuit, the flow would be, in our case, horizontally and vertically down in our little diagram. So let's look at the third case.
Wait. Let's ask a couple more questions.
Yeah.
what happens if they build the bridge incorrectly and the pressure drop is not near zero?
Oh, that's a great question.
Yeah.
So if the pressure drop across the bridge, and again, that's from this point here to this point here, let's say that the delta P, oops, that's supposed to be a P, is, let's say it's some significant number. And let's just, since we're not going to talk about specific numbers, let's just say the delta P is high. Well, in any hydronic circuit, you always have to have a balance in the pressure drop. So if the pressure drop was high, now I'm going to assign an arbitrary value. So let's say that the pressure drop across the bridge was 20 feet. That means that the resistance of the secondary circuit would also have to be 20 feet. So whatever flow would be necessary to have the secondary circuit have a 20-foot pressure drop, that's the flow that would get as a consequence of having a pressure drop across the bridge of 20 feet. So it would induce flow in the secondary circuit, and if it's a true hydraulic separator, we don't want that to happen. So we never want that pressure to be high. Does that help?
Yep. And someone's asking, when would the second case actually happen?
That's a fairly common. So again, let's go back to the primary circuit, and let's go to the secondary circuit here. So typically the primary circuit is constant flow. And in a primary secondary circuit, back in the day, when chillers and boilers, and again, these numbers here are not correct, but chillers and boilers, in order for them to operate successfully, they had to have a constant flow. And so the purpose of the primary circuit was to maintain constant flow, and that's 1,200 gallons per minute. So the secondary circuit, usually the secondary circuit is made up of a bunch of terminal devices that have two-way valves. What do I mean by that? So I've shown a building here, but the piping inside that building, I could have a supply, for example, and let's say the supply has flow from left to right. And at some point, I take a branch off of that supply and maybe go through an air handling unit, let's say an air handling unit coil, and then a two-way control valve. And then I'd be connected to the return line, okay? So we have a bunch of two-way valves here, and as those two-way valves modulate towards the closed position as a function of reduction in load, then we probably have a variable speed drive on the pump, which means that we would have perhaps a flow of, I'm going to say about 20%. Well, 1,200, just check my arithmetic, Brett. If I had 1,200, so I would go from a minimum flow of about 240 gallons per minute up to a maximum flow of about 1,200 gallons per minute. And that would be the range that I would have for the secondary circuit. So as I said a moment ago, case number 2 is when the secondary flow is less than the primary flow, and that typically happens as you back down from your peak demand. In our case was 1,200 gallons per minute. So if the load was anything less than 1,200 gallons per minute, then we'd have a reduction in flow, and that's when the primary is always greater than the secondary. Does that help answer that?
Yeah, and based on what we've talked about in the past, and you have stressed more than once in other presentations, that's most of the time.
Yeah, and you know, in terms of sort of classic basic design, the load on the secondary side varies, or the flow varies, while the capacity, or let's say the flow is a better term, the flow on the primary side remains constant. So the flow on the primary side is constant, and the flow on the secondary side is variable. Big V over here for variable flow. And under those circumstances, assuming that under 100% load and 100% capacity, at 100% load is equal to 100% capacity, so that would be the maximum flow at 1,200 gallons per minute. And then the minimum would be based on some other criteria, perhaps whatever the pump could withstand for minimum flow, which might be around 20%. Okay?
Yep.
All right, and the third case is when the primary flow, all right, is less than the secondary flow. Well, let's try that one out for size. Let's assume for a moment that the primary side over here was 1,200 gallons per minute, 1,200, and then something changed on the secondary side. Let's say somebody added on to our building at some point, and the secondary flow, and I'm just making up these numbers so you can get an idea of what's going on here. Let's assume the secondary flow was 1,800 gallons per minute. Well, how could I get 1,800 out of 1,200? Well, 1,200 comes around the corner, and I'm peeling off 1,800, not 1,200 anymore. I'm peeling off 1,800 gallons per minute. That means that flow across the bridge is now in the opposite direction, and that's going to be 600 gallons per minute. So there's 1,200 plus 18, plus 600 rather, plus 600, let me write that up there, equals 1,800. That's a little goofy, I know, but you get the general idea. And then as that 1,800 gallons per minute comes back toward the primary circuit, we're going to peel off, remember this is 1,800, we're going to peel off 600, and so what returns back is 1,200. And that's when the case when the primary flow is less than the secondary flow. And that's the third case. The important thing to keep into consideration is whenever the primary flow is less than the secondary flow, the flow across the bridge is in reverse. Goes in the opposite direction.
There's a lot going on in that bridge at different times.
Yeah, that's a busy bridge.
And obviously that does affect the temperatures as well, and especially in this case.
Yeah, because I'm not going to put an exact number in there, but if this was let's say this was 44 degrees Fahrenheit in the primary side, well, the secondary side in this case is coming back at 54. Well, if you have 54 degree water at 600 GPM, 54 degree Fahrenheit water at 600 GPM mixing with 1,200, then that means that the water temperature coming back here, I'm not going to do the calculation out, but the temperature would be higher than 54, and I'm just going to arbitrarily pick a number. It's not the right number. I'm just going to arbitrarily pick a number, and let's say, what is that, about 10, so it's about, I don't know, maybe it comes back, and the mixed temperature is somewhere around, let's see, that's 10, 5, 40, maybe it's 47 degrees. Maybe it's in that order of magnitude. Well, as that primary temperature, 47 degrees, as that rises, we have less capacity out to our building, and potentially if the water temperature rises high enough, we run into the problem of not having the capability of doing dehumidification because our water temperature is too high. So whenever the primary flow is greater than the secondary flow, we wind up with the flow across the bridge is in the opposite direction, and we get the wrong temperature for the system. In this case, it starts to rise. Good stuff.
So someone's there's a couple questions. Can you elaborate why the Signorino, oh shit, it just disappeared. When primary is greater than secondary would occur. So you got 1,200 in the primary, and you only have 800 or 600 in the secondary. I think that's tripping some people up again.
So in other words, in our simple example here, we have 1,200 in the primary, and they're saying what happens if we wind up with less than that in the secondary?
Correct. Yeah.
So let's assume that the secondary was 1,000, right?
Yep.
So 1,200 rounds the corner, 1,000 gets peeled off, and then across the bridge would be 200. And then we'd feed the building with the 1,000 as that comes back, 1,000 here. And that would be plus the 200 across the bridge to make 1,200 back here again. So right. Those two values are equal to each other. Did that answer the question, or do you think there was another?
Yeah, no, yes, that's answering it. And one gentleman's asking is, would it be possible to vary the flow in the primary when this case occurs? So instead of it being 1,200, can you slow it down to 1,000?
Oh, that's a great question. Actually, we're going to cover that in a few minutes, actually.
Okay.
But in this case, remember, we're not going to slow down the primary at all. We're just going to say that the primary is constant. That's constant flow. And so whenever we vary the primary flow, that's a different phenomenon.
Okay.
So in a classic primary secondary circuit, the primary flow is constant. And then we're going to talk a little bit about what happens. How do you
Rich,
set up a piping
like right
system?
now.
Say again?
Yeah.
I seem to be losing you, Brett.
Right.
Well, I've lost Brett, so I'm going to go on to the next slide here. Maybe he'll come back in a second. All right.
No. Sounds good.
Okay. Let's see what else we got here. So here's another representation of a primary secondary circuit. It's just a slight variation in terms of how you might see the piping. So in this particular one, again, we have for the primary circuit. The primary
Test.
circuit. I could hear you say test, Brett. Are you back? No, apparently you're having technical difficulties today with sound, so we can only hear you periodically. Well, I'm going to continue, and then I'm going to pause in a second and see if there are any questions that we might have to answer. So again, typically, by the way, the primary circuit.
I don't know.
You're back,
I
Brett.
think I'm back.
You're back now. Did you have another question? Now you're not back. Okay, well, unfortunately, that's one of the challenges that we're faced with technology. So the point I wanted to make is typically the primary circuit is associated with the device that's doing the either heating or cooling. The secondary circuit is generally referred to as the system that is supporting the load. And over here on the left is the bridge. Again, one more time. It's a little bit different than what we showed you in the previous. However, the principles are still the same. Again, we could have the secondary circuit 1,200 gallons per minute, and the primary circuit 1,200 gallons per minute. Primary is equal to the secondary. And again, if we allow the the secondary circuit to drop, let me just erase that one little thing there. Let's erase this here. If we allow the secondary circuit to diminish, let's say it drops down, and again, let's make that 600 gallons per minute, then what happens is that across this bridge right here, that would be 600 gallons per minute. So let's put that 600 up there. So it's just a slightly different way of looking at the same problem with a slightly different piping configuration. And this might be a little bit easier, not easier, but a little bit more familiar to what most people would see for a piping system. Okay, now another thing we can do, this is sometimes referred to as a field designed hydraulic separator, but there's another option. The other option is that you can go with a prefabricated or pre-engineered hydraulic separator or bridge. And if we did that, it would look like this. So this little guy right here is a hydraulic separator. It's a pre-engineered device. There's the primary circuit on the right, the secondary circuit on the left. And instead of having just a pipe connecting the primary and the secondary circuit, we have this little guy here, which is called a hydraulic separator. And that's a pre-engineered device that DECOUPLERS manufactures. We're going to get into what that looks like in a minute. I'm going to pause for a second and look to see if there are any questions, because I think we lost Brett. So I'm just going to go back here to the questions tab and pull that over here. And I'm going to see if we have any last minute questions, because, okay, let's see. It says, let's see, are flow meters the only controls recommended for a bridge? Actually, you don't actually have to monitor the flow across the bridge, as long as when you set up the balancing between the primary and the secondary circuit. Remember that they are hydraulically separated in the sense that the flow in the primary circuit does not influence the flow in the secondary circuit. And the opposite is also true. The flow on the secondary circuit does not influence the flow in the primary circuit. So if both circuits are properly balanced, then you actually don't need to have flow meters, because once they're balanced, then as you change the load on the secondary side, you would be modulating the flow, usually as a function of a variable speed drive in the secondary side. Okay, someone has asked a quick question here. It says, what is the advantage of the pre-manufactured separator compared to the previously shown piping arrangement? So that's actually what I was going to get into next. Let me see if we can erase the screen here. And oh, yeah, we did go on to the next thing. Okay. So here is a picture of a hydraulic separator. Just move some information around here. So here is a pre-engineered hydraulic separator. And again, similar to what we said before, let me draw some things over here. I'm gonna move some stuff around. Bear with me 1 second while I make a little space on my screen here. My mouse is not cooperating. Look at that. Boy, I tell you, when the technology goes cuckoo, it really goes cuckoo. All right, here we go. All right, so let's assume that on the left side is the primary side. So I'm going to go over here and get is the primary side. Let's call this the primary side and the secondary side. So there's the primary inlet and the primary outlet. Primary side, secondary side, and there is the secondary inlet and the secondary outlet. Now, because this is a hydraulic separator, it's a pre-engineered, pre-configured device. It has several critical dimensions, and those dimensions are the diameter. I'll just sketch that out here. Say the diameter of the hydraulic separator, the distance between the inlets and the outlets here. And if you notice inside this cutaway, we have a little baffle. So a pre-engineered device takes into consideration, oh, and the other dimensional critical dimensions are the dimensions from the total length of the hydraulic separator to the connection. So all of these different dimensions are important in terms of their design for the hydraulic separator to work properly. So the advantage to having a pre-designed thing is that there's no guesswork involved. You just basically pipe it up, you put it into the proper primary, secondary piping arrangement like we had over here. Again, this is primary. Let's put in here on the primary side, let's put out over here. And then on the secondary side, let's put in the bottom and out at the top. Okay. As long as you just connect the piping and it's the right size, then the hydraulic separator works. It also can double as an air separator because we have this air vent at the top. So you get kind of a dual function. It's not an air and dirt separator per se, but it can be, which I'm going to show you another option in a minute. So it looks like we have a couple of other quick questions. I think we've lost Brett completely. Brett, if you can still hear me, even though you might be having microphone problems, can you type into the question area that you can still hear me okay? Okay, I'm going to wait for, I'm going to continue on here. I did get a question here from Mario. It says, do you size it by flow or pipe size? Actually, you size it by flow. And I'm actually going to show you that in a few seconds here. Okay, so that's called our Flex Balance 5900 over here. And now we can add another feature. Let me erase this stuff here. Let's go to the next slide. And in the next slide, we have an added feature. Let me just hold on 1 second while trying to grab my, it's amazing how the technology wants to sabotage everything you do. Okay, let's do that. So if you notice the little picture on the right is almost identical to what we had before, only this time we have the basket with the Paul rings, and we have 2 sets of baskets. And that means that this hydraulic separator, which is called the 5900 flex balance, and we have the word plus in there, acts as not only as a hydraulic separator, but it also acts as an air vent at the top and a blowdown at the bottom. So it's an air and dirt. So it's a 3-function device. It's a hydraulic separator, it's an air separator, and a dirt separator. And so now you can use this device, and instead of having 3 separate devices, an air separator, a dirt separator, a hydraulic separator, you can have them all integrated into one device. Okay, now let's look at some of the sizing challenges here. Just hang on there 1 second while I move some stuff around. Okay, here we go. I'm going to erase that. And let's look at some dimensional information. If you remember what I said a few minutes ago, what's important here is all of the dimensional information. And it's important, it's critical to have the right overall height of this device, the distance between the connections, and then obviously the connections to the top and the connections to the bottom. So for a pre-engineered device, we figure out all of that stuff based on the size of the unit and how many GPM each one can handle. So I'm going to actually go into, I think I have in my next slide here, the actual sizing chart. Let's see if I did that correctly. Yeah, there it is. Look at that. I actually did that correctly. So if you'll notice, let me go back a few slides because I want to emphasize something here. Just go back here. See if I can get this to go back. Yeah, there we go. Do you remember my diagram over here? Let me just erase a bunch of stuff here. If you'll notice, we have 1,200 gallons per minute in this system. That's the maximum for the primary and the secondary side. And it looks like the pipe size is 8 inches in this case. All right. So let's look at the sizing chart and see what the 1,200 gallons per minute is going to come down to. So if we first said, well, look, we have an 8-inch pipe. So there's 8-inch pipe right there. Is that the proper size unit that we should put into this system? Well, if you go all the way here to the right, you'll see where it says optimum flow. And the optimum flow for an 8-inch hydraulic separator is 896 gallons per minute. Well, that's the maximum flow that we want, but our system has 1,200 gallons per minute, 1,200 GPM. So we would not use an 8-inch. We'd have to go to a 10-inch. If you notice, the flow for a 10-inch is 1,409 gallons per minute. And that's greater than the 1,200. So the actual size that you would need would be a 10-inch instead of an 8-inch. So even though the pipe, put that note here, the pipe is 8-inch, the hydraulic separator is actually going to be a 10-inch because we have to have enough to maintain this 1,200 gallons per minute. So to answer Mario's question earlier, is it based on flow or size? And you actually have to look at this chart and make the appropriate selection based on the flow in gallons per minute. I still don't hear Brett.
Wait, can you hear me now, Rich, or not?
I can, yes, you're back.
I rebooted, I closed out, oh boy. You know what it's like sometimes.
Yeah, the technology is, it definitely wants to bite you in places that are going to cause you pain. So, yep. Yeah. So it's great to have you back.
Yeah, one great question from Tay out in Alaska is, what is the pressure drop across our hydraulic separators?
So the pressure drop, I'd have to go into our selection, our software, but it is negligible. It's relatively low. And maybe,
yeah,
Brett,
I can look that up.
Seconds, you could look that up and we can give someone a more definitive answer.
Here's a great question, Rich. You were talking about air and dirt separation And this comes up quite a bit. How often should dirt be removed in a chilled water or heating water system?
That's a great question. And it actually turns out the answer, let's say it's the chilled water for a moment. So chilled water is generally speaking, most chilled water systems are designed to be a closed loop pressurized system. And initially, when you start up these systems, we have startup strainers in the air and dirt. I'm sorry, we have startup strainers in the end suction diffusers. But most engineers will have information in their specification that says the system has to be flushed and strainers have to be cleaned before the system is turned over to the either the owner or the long-term operator. And the point that they're trying to make here is that the system has to, the water or the solution, in this case, it could be water or water glycols, the most common, is that it needs to be as clean as possible. And so once you get the initial circulating and you clean out the system, you add the chemicals and all of those other maintenance related things, then what I recommend is that you blow down your air and dirt separator, you open the valve at the bottom of the air and dirt separator once a day for a few minutes to check the, to how clean is the water coming out. And then once you start getting clear water, then usually you can go to blow down, say once per week. And then once you start getting clear water after each week of blowdown, then you go into a schedule that's recommended by usually the chemical, the company that's providing chemical treatment for you. Then they can make recommendations because it has a little bit to do with how much makeup water is coming into the system and what the dissolved solids are. And that's very, very specific to a job site. So, but initially, every couple of days to clear out what's in the system, and then maybe go to a week and then a weekly interval, and then to go to a longer interval to work with your chemical treatment company to see what's appropriate. Any other questions, Brett?
No, go ahead.
Okay. See, how are we doing for time here? Yeah, we're actually doing pretty good for time. All right, so let's look at another device. And this other device here is called a multi-purpose tank, MPT. And one of the ways that you can get a multi-purpose tank is you can get it as a hydraulic separator, combination air and dirt separator, all in one device. The way this particular one is piped up, you can see it has 4 connections. There's the primary, let's make this the primary side in and out. Make that an arrow. That's not the best arrow in the world, is it, Brett? Let me try erasing that and try it again. Sometimes I get carried away. Okay, so there's let's say the left side is the primary side. There's the flow coming in and out. And then say the right side is the secondary side, and there's the flow coming in and out like that. So you can get a multi-purpose tank, which not only, in terms of traditional multi-purpose tanks, they might be a buffer storage tank, might be a variety of functionalities. But you can also get it configured as a hydraulic separator, and you can add Paul ring baskets in here. I'll make a bunch of Paul rings inside a basket. And you can get it to operate as an air vent. There's an air vent as an air separator, a dirt separator, and a hydraulic separator. So multi-purpose tanks have, as the name implies, multi-functionality. Now, one of the things I want to caution against is that multi-purpose tanks, when it comes to chilled water, you have to look very carefully at the configuration for a chilled water system, because a multi-purpose tank, if the diameter is too great, this diameter down here, if the diameter of the tank is too great, you may get some premature mixing that you don't want to happen. So, so chilled water is a little bit critical, so you have to look at that carefully and make sure that you're not going to get any mixing. Generally, hot water, you can withstand some mixing, and it's not going to be detrimental to your operation of the system. So hot water is okay. Chilled water, you must check with the factory and make sure that it's not too large a diameter to operate without a lot of mixing.
Is this another way to add volume to the system as well?
Yeah, that's an excellent point. So if you had the need for having system volume, let me go back to my handy dandy. Let me go back to my handy dandy whiteboard here. Where is my white? Oh, here's my whiteboard down here. Okay, so we can take my previous whiteboard and we can erase a bunch of stuff. Look how easily that erases, Brett. All right, and so let's remind the audience, what was the question again? Can you use it as a buffer tank?
Buffer tank, yes. Well,
Yeah.
does it add volume to the system?
Does it
Yes,
add volume? Yes, it adds volume. So let's say that you had, again, you had a chiller and you had a primary circuit like this. Let's put a circulating pump in there. And then this is the secondary circuit. So one possibility, let me use this line here. One possibility is to put in your multi-purpose tank. And now you have a primary circuit on the left side, and then you have on the right side the secondary circuit. And there's our load again, like we had before. Whoops. Oh, I didn't mean to do that. That got a little crazy, didn't it, Brett?
Well, I've seen loads installed like that sometimes. So.
Okay, so there's our load. I'll just put a letter L there. And there's our secondary circuit. So there's our multi-purpose tank. So a lot of chiller manufacturers will say, okay, if you put a chiller in a hydronic system, we want to make sure that there's enough water volume. So chiller manufacturers have to provide you with the water volume for their specific chiller. But just to give you an example, let's say that let's say that our system happened to be 2,000 tons. I'm just making up a number here. 2,000 ton system, and the chiller manufacturer is telling us that they want to have a minimum volume of 5 gallons per ton. Now that number varies from chiller manufacturer, so we always recommend that you get the actual number. So that means that the total system volume wants to be 10,000 gallons. And let's assume that between the primary circuit and the secondary circuit, the total amount of volume of the system is somewhere, and I'm just arbitrarily making up a number. Let's say it's 8,000 gallons, 8,000 gallons, and that's from the system volume. So I'll put that in there, system volume, not including the multi-purpose tank, system volume. And if I subtract the total volume that's required by the manufacturer, there's the total, and the system volume, well, let's put SV for system volume. Multi-purpose has to have a volume of 2,000 gallons. So that's how we figure out how big the multi-purpose tank needs to be. Now, again, the important thing to keep in mind is that I picked a number that is commonly used in the industry, but it's not the only number. I always recommend you go back to the chiller manufacturer and you get the actual gallons that the chiller manufacturer is looking for. And by the way, the same thing holds true for boilers. Boiler manufacturers are also looking for a minimum amount. So this multi-purpose tank can work as, I'm going to abbreviate this, as a hydraulic separator, as a buffer tank, as an air and dirt, and it has all three functions.
So if you think about it, right, from a simplicity standpoint, you specify something like that, it takes care of all of those components. Your bridge is installed correctly, and you don't need air and dirt elimination on either side of the primary, secondary, or both sides.
That's right.
I mean, there's a lot of inherent benefits to what you just wrote with those three items up top there.
That's right. And I, again, as I say all the time, you know, you never do this kind of design work in a vacuum. You also always make sure that you have the appropriate configuration and sizing based on manufacturer's recommendations. So, hey, Brett, we have about 5 minutes left. Do we have any
Yeah.
other questions you want to pose?
Yeah,
up?
let me throw a couple out at you. Design install. Are there any recommended lengths of pipe, straight runs at the inlets and outlets of an engineered hydraulic separator? I don't think so. Right, Rich?
Well, you know, the truth of the matter is that the longer the straight run of pipe is, the more likely you are to have laminar flow in and out of the hydraulic separator. So you want to try to maintain, you know, somewhere between 5 and 10 pipe diameters. Now, I already know that in most installations, you probably can't obtain 10 pipe diameters. But, you know, the closer you can get to, say, 5 pipe diameters on the inlet and the outlet, the more likely you are to have laminar flow, and the better the device will operate. So it's one of these things where, you know, we know that you can't get 10 pipe diameters, but you also have to recognize that the more the turbulent flow is, the more, the less efficient, I don't want to use the word efficient, the less capable the hydraulic separator is. Does that sound like a goofy answer?
It's a roundabout way of saying efficient. But so one more time, we got 4 minutes. If you have 1200 GPM constant in your primary and a zone secondary doing a variable from 4 to 600 GPM, what's the flow through?
Let me bring up my
for the last time, we got to see the beautiful whiteboard.
The whiteboard, yeah. So let's erase all this stuff here. We're gonna,
you know what's nice about that eraser? It doesn't affect my. I don't hear it squeaking, so it doesn't. You know, I don't get.
I know it's like there's another way to erase, which is here. I'll show you in a second here.
Yeah.
There's another way to erase, which is more efficient. That's if we use this little loopy thing over here.
Oh.
Isn't that cool? And then we can just delete stuff.
Yeah. As usual.
Yeah, there we go. We can delete that. I put it in the basket. Okay, so let's ask the question, and I'll make a little sketch here.
So you got 1200 in the primary.
So I'm going to oversimplify this and just have our primary look like this, right?
Yeah.
There's our primary circuit.
Yep.
And we had 1200 in our primary circuit.
And draw a box because we have the 4900 there, 5900.
So there's the hydraulic separator. Well, we want something that's a little bit more representative of a hydraulic separator, right?
Yeah, with 4 connections.
Yeah, so let's put the hydraulic separator in there like this, and let's have the 4 connections. This is the chiller over here. This is the primary side, and this is the outlet here, the inlet here. There's the outlet there and the inlet here, and then obviously we have to have a pump on the secondary side. This is the secondary side, and then the load. Okay, and now what was the question one more time?
So if you have 600 in the secondary,
yeah,
can you just go over the flows again? I mean, it's the same as what you started with, pretty much. I mean, but what's going through the
what's going on inside the hydraulic separator is that we'll have 1200 gallons per minute on the primary side, 600 going out on the secondary side. That means in this direction inside, there's going to be a flow of 600. And that 600 plus what's coming back here equals a 1200. So that's what comes out on this side. So the flow inside the hydraulic separator, 5900, is going to be in the, it's mounted vertically, so it's going to be in the downward direction.
And then obviously, if it was a variable speed system and it was going from 400 to 600, that if you had 400 in the secondary inside the hydraulic separator, the 5900, you would have 800. I mean,
that's correct. Yeah. So if we just simply erase these numbers here, and then we put a different ratio in there, just like you said, if you had 800 out here, then you would have 400 across here. Or if you had 400 over here, you would have 800 across here.
Yep. That answers the question.
Okay. Anything else?
Nope. I think you've covered it all, my friend, as usual.
Well, I realized that there was a lot of material to cover here, but hopefully you've got a better idea of how a hydraulic separator works. And as we said at the beginning, it has a variety of different names, but they all mean the same thing. I have always wondered why in our industry we have multiple names for the same thing.
Yeah.
But when you have different names for the same thing, it's confusing because people think that it might be different. But yeah, that's just the way it is in our industry, I guess.
Yep. I remember over 25 years ago when I started, I'd sit in meetings and I'd catch this terminology and I'd look it up. I understand it. And then I go into the next meeting and they change the terminology. We meant the same thing, but I was lost.
Yeah, it's
You
now
know,
I have to admit when I go to some of the you know the sales meetings and they use words
right.
like sales and orders and EBITDAs and all, I get confused.
Yeah.
Thank God I'm working in a simple field like engineering.
Oh, great job, Rich. Thank you as usual. You did a great job. You want to say goodbye?
Yeah, thanks so much, everyone. We had a great turnout. I think we had at some point there, we had over 180 people.
Yep.
And actually, it shows on the computer, even though a few people are leaving, we still have over 180 people out there. So that was really, really great. Thanks so much for everyone participating. Hopefully you got something out of it, and you'll join us in the future for some additional commercial-focused TACO Tuesdays, as we like to call them. Thanks a lot. Take care. Back to you, Brett.
Great job, Rich. And you're getting a lot of thank yous and great job in the question/comment section. So we
Oh, yeah,
appreciate
I should mention, Brett, is maybe you were already going to mention this, and I apologize if I cut in, is
Yep.
that if you have additional questions, just contact your rep. They can usually answer 99% of the questions. Actually, they can answer 100% of the questions, but once in a while they pretend they can't, and they call Brett and I. But they already know the answer when they call us, right, Brett?
That's true. Usually they tell us the answer, even when
Yeah,
they
they
call.
do. They tell us the answer, and then we just have to shake our heads and say, yeah, that's true.
Best rep network in the industry. TACO's rep network, bar none, by any stretch. But thank you, Rich. Great job. Look for your emails tomorrow. 2 weeks from today, we're going to talk about HVAC hydronic pump fundamentals. So see you in 2 weeks, everybody. Take care. Bye now.